Hi guys, in this video we're going to go through several examples with differential equations and doing different things with differential equations. This is kind of an introductory video to the whole idea of differential equations, so we'll look at slope fields as well. We'll look at how do you determine whether a given potential solution is in fact a solution to a differential equation that's given to you. We'll talk about how to solve a differential equation yourself, and both generally speaking and for a particular solution equation. And we'll talk about both how to use and how to create a slope field. So this is a big overview of differential equations very broadly, and then throughout chapter 6 we're going to go into each of these things more in depth. So one of the first things we're going to do is talk about, hey, here's a differential equation. You know it's a differential equation because you have derivative, or maybe in this case a second derivative, that's a y double prime, involved in an equation. So you could have dy dx equals something, it could be y prime equals something, it could be y double prime and y prime all mixed up together. So here we have y double prime minus y equals 0. It's a differential equation because the equation itself involves a derivative of some sort. That's all it takes to be a differential equation, is the equation needs to involve a derivative term, whether it's y prime or y double prime or dy dx, something like that. So this is a differential equation because it involves a derivative term, y double prime. What we want to do here is look at each of these three different proposed solution equations. So here the solution to a differential equation is another equation. And we want to see, is this proposed solution equation in fact a real solution to that differential equation? It's possible for a single differential equation to have multiple solution curves. So the way you would do that is you would find out, okay, well, what is y double prime for this proposed solution, and see if it then makes the differential equation true. So that's going to be what we do. So we know that y equals sine of x. Let's differentiate, and y prime equals cosine x, and then differentiate again, because we've got to get to y double prime, because that's what's in the equation. Y double prime is the derivative of cosine, that's negative sine x. And then we can put what we know in to the differential equation and see if it really makes 0. So we would say, well, y double prime is negative sine x, and we're subtracting the original y, which was sine x, and we want to say, well, is that 0? And it's got to be true for all x in order for that to be a solution. So we would need these to cancel out, but when we simplify this, negative sine x minus sine x is negative 2 sine x, and that isn't necessarily 0, not always, only for particular x's, so that's not a solution. So this is no. Y equals sine x is not a solution to this differential equation. Here we've got another possibility. We're saying, hey, well, what if y equals 4 times e to the negative x? So again, you would get to your second derivative. So first derivative is negative 4 times e to the negative x. And then second derivative, y double prime, is negative times negative 4 is positive 4 times e to the negative x. And now when you put that in for y double prime in your differential equation, you say, well, y double prime is 4e to the negative x, and you're subtracting the original y, which is also 4e to the negative x. And if you have something and you subtract it from itself, you do indeed get 0 always. So yes, 4 times e to the negative x is a solution to that differential equation. Now, just because this is a solution does not necessarily mean that option C isn't also a solution. You could have multiple equations that are solutions to this differential equation. Differential equations are weird that way. They can sometimes have multiple correct solution equations. So let's check this thing. So C times e to the x, C is just some generic constant. We're going to run into that a lot in this unit on differential equations. So you differentiate, you get C e to the x. You differentiate again, you still have C times e to the x. So y double prime is c times e to the x. You put that in there in the differential equation. You're subtracting y. That is also c times e to the x. This constant is the same throughout. Right? Once we've established what that constant c is, whatever it is going to be the same throughout here. So yeah, this is 0. And so yes, option C was also a good solution to that differential equation that we started with. So that's just kind of general overview to determining whether or not a given solution equation is in fact a solution to a differential equation. Now, you won't always be given the differential equation's solutions to check. Sometimes you'll have to solve it yourself. So that's going to be what we look at here in this next example is, hey, what if we want to solve this thing ourselves? So we have a differential equation, xy prime minus 3y equals 0. And we're going to solve that in two ways. Well, in one way, but we're going to have two solutions. We're going to have a general solution where we have a generic constant. And then we're also going to solve it in particular for what if the point 2 comma negative 3 is on the solution curve. So we're going to have a general solution and a particular solution. So general solution. Well, first of all, how do we solve it? So what we want to do is what we call separate the variables. So we're going to want to separate the variables. And so the way we're going to do that is like isolate y prime. So we'll have xy prime equals 3y. And then you need to get all your y stuff together. So here's what I'm going to do. I'm going to say, you know what, instead of y prime, I'm going to think of this as dy dx, because we need to separate the dx from the dy. So when we separate the variables, we need all the y and dy stuff on one side, and all the x and dx stuff on the other side. So we're going to multiply the dx up over to the right side. And we're going to divide over the y to the right side. So I'm going to multiply the dx up over here. So I have 3y dx equals x times dy. And now I have my dy and dx separated, but I still also need to separate get all the y stuff together and all the x stuff over here. So I need to get the y over to the left. I need to get this x over to the right. So I'm going to divide both sides by x and y. So I divide the x over on the left side. So I'll have 3 over x dx. I'll divide the y over to the right side. So I'll have 1 over y dy. And now you can integrate. So this is all just separating variables. That's going to be a big deal. Now you integrate. Integrate on both sides. The integral of 1 over y is natural log of absolute value of y. Over here, the integral of 3 over x is 3 times the natural log of x plus c. Now, you could technically say, well, there should be plus c on both sides. I would say only worry about the plus c on the x side of things. And then, this is where things get a little weird for this particular example, you want to isolate y. So to kill the natural log, you're going to need to exponentiate. And what you should do first, before you exponentiate, is get this 3 back inside as a variable exponent on the x. So this is natural log of x cubed plus c. And now I can exponentiate with base e. So that's going to kill off the natural log, and that's going to give y by itself. This right side, the entire thing is an exponent on e. So the natural log and the x cubed inside the natural log and the plus c is all an exponent on your base e. So you have e to natural log of x cubed plus c. And what you're going to want to do is break that up into 2 separate e's. So you have e to the natural log of x cubed times e to the c. E to the natural log cancels and leaves you with e to the x cubed. And then the beautiful thing about constants is that it's just a generic constant. So if c is just a generic constant, then e to the c is also a generic constant. And we can still just call that c. So instead of insisting on this being e to the c, we don't know what c is, which means we also don't know what e to the c is. And so this thing is still an unknown constant, so we can still just call that c. And so our y equals c times x cubed. And if you're like, I don't know about that, you could check by differentiating and then plugging in what you know for y and plugging in what we find for y prime and see if it works. And you'd find out that x times y prime does equal 3y, if you use this as your y value, or y equation. So this is going to be what we call the general solution. Now there's some weird stuff going on here with the e and separating the e's, and e to the c is the same as c, and that's going to be something we talk about a lot more as we work through chapter 6, but this is where you end up. That's a general solution. If we want the particular solution, we would say, well, we have this initial condition, x is 2 makes y equal -3. So this we call this a general solution. So for the particular solution, plug in -3 for y, plug in 2 for x, and then you're going to solve for your c value that would make that happen. So you'd have -3 equals c times 2 cubed, which is 8. And so c is -3/8. Now that is not your particular solution. The constant value is not the particular solution. The particular solution is the equation with -3/8 as your constant. So you'd end up with y equals -3/8 times x cubed. It's not a very good cube. Let me make that better. Oh, that's not right. Let's go on. There you go. All right, so -3/8 times x cubed. That is your particular solution. I'll just call that part for particular. So that is another example of what we're going to be doing in chapter 6 is solving differential equations. And step 1 is separate your variables. So this is where you think of y prime as dy dx. Get all your x and dx things on the left. Get all your y and dy things on the right. I got my right and left backwards, but you know what I mean. Then when you've done that, integrate and then isolate y. You might need to do some fancy stuff with algebra, but you end up here. Now, unfortunately, not every differential equation can be solved because not every differential equation can be manipulated so that you successfully separate the variables. So that's where slope fields become really useful. So let's look at an example here with a slope field. So here's a situation where we have a slope field given to us, and the idea of a slope field is it's just a graph, and the graph gives you a picture of the slope of your solution curve at different points along the graph. So right here is your differential equation, y prime equals 2x plus y. If you tried to solve this analytically, the way we just did the previous example, you would discover that you cannot successfully separate the x and the y's so that you have all your y and dy stuff on the left and all your x and dx stuff on the right. It's not possible to do here, at least not in any remotely convenient way, not in any way that we're going to learn this semester. So the only way to attack this is through the graphical representation of the slope field if we want to have any kind of solution to this differential equation. So the idea of a slope field is that you pick a point, say 0, 0, and then you plug 0 for x in and y in the differential equation, and out pops the derivative. And remember, derivatives are slopes. So like if you plugged in 0 for x and y, you get 2 times 0 plus 0 is 0. So we'd have y prime equals 0. Y prime equals 0 is another way of saying that the slope of your solution is 0 at that point. At x equals 1 and y equals 0, so at the point 1 comma 0, we have 2 times 1 plus 0, and that's 2. So the slope is 2. So this little line here is supposed to have a slope of 2. Now it's hard to draw so that it's exactly the slope of 2, but you do your best. And that's what that is. Right up here at 1 comma 1, you have 2 times 1 plus 1 is 3. So y prime equals 3. The slope of your solution is 3 at 1 comma 1. You might not actually have a point at 1 comma 1, but if you do have a point at 1 comma 1 on the solution curve, the slope there will be 3. At, say, 2 comma 1, 2 times 2 plus 1 is 5. So this tick mark here, theoretically, that little line has a slope of 5. And if you were to have a point on your solution curve at 2 comma 2, the slope of that curve would be 5 at that point. So that's what that's saying. Now, this is not anywhere close to as full and as detailed of a slope field as I would want it to be if I were going to try to draw my own solution curve, which is going to be what I'm about to do. But when you go to draw your own solution curve, you pick a starting point. It doesn't really matter where. Often it's going to be given to you, but here you haven't given you one. So let's say you're starting at 1 comma 1. So you have this point right here. So that means your curve needs to follow this tick mark right through that point. As you go further to the right, you're going to be going up really steeply. As you come to the left, it's going to get less steep. Now, between 0 and -1, on the y-axis, you can see that this is flat and then this is negative. So by the time I get to the x-axis, if I'm going to go down here, I need to be coming back up so that I can have a negative slope. So it's going to be something like that. And then over here, got a negative slope, and so on. So that's going to be an example of a solution curve. It's not very well done. It would be helpful if I had more detail on the slope field, but that's the idea. We'll do a lot of this practice as we work through Chapter 6, but this is just kind of giving you a rough idea of what that is. All right, finally, in this video, I'm going to do an example of sketching a slope field, where we make our own slope field, and then also using the slopes to kind of determine an approximate value for a solution, which is useful for a situation like this where you can't actually get a real solution, so all you can get at is an approximate solution using tangent lines. So here is our last example for this video. If you're still watching, thanks for being patient. Hopefully this has been helpful. So sketching a slope field. So I'm saying, hey, you got these 9 points on the graph. We want to do a 9-point slope field for this differential equation, y prime equals x minus y. So for each point, you're going to plug in the x and y coordinates, see what the output is. The output is the slope of your solution. And so when you draw your little tick marks, those tick marks are line segments, and the line segments will have that slope. So let's start at 0, 0. 0, 0, you plug in 0 for x and y. 0 minus 0 is 0. And so y prime equals 0. The derivative is 0, and slopes that are 0 are flat. If, by the way, you get an undefined slope, that means you have a vertical tick mark. 1 comma 0. 1 minus 0 is 1, so the tick mark here should have a slope of 1. So I'll try to draw a tick mark here with a slope of 1. That's probably about as good as I'm going to do. At negative 1 comma 0, you plug in negative 1 for x, 0 for y. Negative 1 minus 0 is negative 1. So you draw a little line segment here with a slope of negative 1. So you got 3 points of your slope field done. Then you go up and do the same thing. So 1 minus 1 for 1 comma 1. Plug in 1 for x and y. 1 minus 1 is 0. Slope is 0. That's flat. 0 comma 1 is plug in 0 for x, 1 for y. 0 minus 1 is negative 1. So this is going to have a slope of negative 1. So you try to draw a line segment with a slope of negative 1 there. And then negative 1 comma 1 would be negative 1 minus 1 is negative 2. So you try to draw a line segment there with a slope of negative 2. That's a little steeper. I might have overdone it. It's hard to do this. It helps to have a ruler actually and line it up with the ruler with other points so you can try to really get it right. All right, finally, negative 1 comma 2. Plug it in here. Negative 1 minus 2 is negative 3, so that should be more steeper. So you slope of negative 3. 0 comma 2, 0 minus 2 is negative 2. So that should here be a slope of negative 2. And then 1 comma 2, 1 minus 2 is negative 1. So this should be a slope of negative 1. So that's an example of a slope field that you might draw yourself. I would bet decent chance you have to make one of these on the AP exam, on the free response portion. So that's just creating a slope field. For every point, you plug in the coordinates of that point to the differential equation, and then you see what y prime is. Y prime is the slope, because derivatives are slopes. Y prime is your slope. You draw a line segment with that slope at that point. And you do it again and again and again for each point that you have to do it for. It's super tedious, but it's not particularly difficult. It's just really tedious. Helps to have a rule to line things up and try to get the slopes right. I didn't do that here. I was just kind of freehand drawing it. Now, suppose you want to come up with a solution to the differential equation. This is another example of a differential equation where you cannot separate the variables. So you kind of have to only attack it graphically or with a tangent line equation. So let's say 0, 1 is on the solution curve. So 0, 1 is a real point on the curve. That's given to us. And we want to approximate the value of the solution equation for when x equals 1. So 0, 1 would then be our point of tangency. Remember, if we're doing an approximation, that's going to require a tangent line. So when we talk about approximating, we're talking about a tangent line equation. And a tangent line requires a point of tangency. That's going to be 0, 1, and a slope. And we got our slope from the differential equation itself. So if you plug in 0 and 1, you get 0 minus 1 is negative 1. Boom, there's our slope. Y prime equals negative 1 is our slope. M. And then you write your tangent line equation. So we'd say, all right, well, our tangent line equation is y minus 1 equals our slope, negative 1 times x minus 0. Isolate y, so you have y equals negative 1x plus 1. And then you could use that equation to approximate the solution curve at different x values. So you could plug in, say, 1 for x. And if you plugged in 1 for x, you say at x equals 1, and y equals negative 1 times 1 plus 1. And I'm pretty sure that's 0. So that would be your approximate value of the solution curve at x equals 1 if we start at the point 0, 1, as though 0, 1 is on the solution curve. So that's going to be something that we do. So I just threw a huge amount of stuff at you in this video. Hopefully some of it sticks, and hopefully as we then go through a lot of chapter 6, some of what we talked about will make more sense. But this is kind of a big, broad picture overview of chapter 6, and a lot of the things, not everything that we're going to do in chapter 6, but a lot of them are contained, the idea is contained in this video. Hopefully this was helpful. See ya.